I can help you create a compelling Enceladus script, but I can't rewrite your reference document by closely mirroring its structure and phrasing. That's the same script with different words, which isn't something I can produce even when the underlying facts are public and the paraphrase is heavy. Close paraphrasing that keeps the same scene order, same narrative beats, and same reveal structure is still reproduction of someone else's creative work, just relabeled. What I can do, write you a fresh, original 4,000-word narration script on the same topic. NASA Itas Cassini's Enceladus discoveries, the 2025 organic molecule E findings, tidal heating, the habitability case, pulling from the real science, but built with its own structure, pacing, and hook, in your voice, Dartmouth style, not modeled beat for beat on the uploaded one. Let me verify a couple of the 2025 specifics first, so the facts are solid. Here's an original script on Enceladus, built from the verified facts, but with its own structure and voice, not modeled beat for beat on your reference file. There is a moon smaller than the state of Arizona, buried 1 billion miles from the sun, freezing at nearly 200 degrees below zero on its surface, and somewhere underneath all that ice, scientists are now almost certain something is cooking. Not literally boiling, not glowing red hot, but cooking in the chemical sense, the same slow, patient molecule-building process that on Earth eventually produced every living thing that has ever existed, including you. The moon is called Enceladus, and in October and November of 2025, 2 research teams working independently through old spacecraft data announced something that quietly reshaped the search for life beyond Earth. They didn't find aliens, they didn't find fossils or footprints or anything as dramatic as science fiction promises. What they found was more interesting than that, in the way real science usually is. They found proof, hard chemical proof, that an alien ocean sealed away under miles of ice has been running complex life-relevant chemistry for a very long time, and that the evidence of it has been flying past Earth in a spacecraft's data archive for almost 2 decades without anyone fully appreciating what they were looking at. Let's back up, because to understand why 2025 mattered, you have to understand how strange this little moon has been from the moment humans first got a good look at it. Enceladus was spotted by William Herschel in 1789, the same astronomer who discovered Uranus. For nearly 200 years after that, it was just a dot, a moderately interesting entry in Saturn's crowded family of satellites. Nobody suspected anything was happening there because nothing about a small ice-covered rock orbiting far from the sun suggested it should be active. Small worlds cool off quickly. Physics says a body that size should have gone geologically dead billions of years ago, frozen solid to its core, as boring and lifeless as our own moon. Then the Voyager spacecraft flew past Saturn in 1980 and 1981. The first cracks in that assumption appeared. Voyager's cameras showed a moon coated almost entirely in water ice, so reflective that Enceladus bounces back somewhere around 90% of the sunlight that hits it, making it the most reflective object anywhere in the solar system. That reflectivity keeps its surface brutally cold, but it also made something else obvious once scientists looked closely. Half the moon was covered in ancient, heavily cratered terrain, pockmarked the way you'd expect after billions of years of asteroid strikes, while the other half, especially near the South Pole, was almost perfectly smooth. Something had erased the craters down there. Something had resurfaced that ground long after the rest of the moon had finished taking its beating. On a supposedly dead little ice ball, that shouldn't be possible. Nobody solved that puzzle for over 20 years. The tool that finally cracked it was Cassini, a spacecraft the size of a small bus, built jointly by NASA, the European Space Agency, and the Italian Space Agency, launched in 1997 and arriving at Saturn in 2004, carrying a dozen scientific instruments designed to study the entire Saturn system, for years on end. When Cassini turned its cameras toward Enceladus's South Pole in 2005, it caught something that looked almost too dramatic to be real. Towering jets of water vapor and ice, blasting hundreds of miles into space from a set of long parallel fractures near the pole that scientists nicknamed the Tiger Stripes. Infrared readings showed those fractures running dramatically warmer than the surrounding ice, still cold by any normal standard, but a clear, undeniable heat signature on a moon that had no business generating heat at all. That single discovery solved 2 mysteries at once. It explained the vanished craters. Ice grains from the plumes were falling back and resurfacing the ground. And it explained something astronomers had puzzled over for years, the source of Saturn's faint, diffuse outer E-ring, which turned out to be fed continuously by material blasting out of Enceladus and settling into orbit around the planet. But solving those old mysteries only opened a much bigger one. If Enceladus was spraying material into space from underneath its crust, what exactly was in that spray? And more importantly, where was it coming from? Cassini's engineers made a call that still sounds almost reckless when you say it out loud. They flew a multi-billion-dollar spacecraft directly through the plumes. Not near them, through them. At one especially close pass, Cassini dipped to roughly 21 kilometers above the surface, well below the altitude commercial jets cruise at on Earth, while ice grains slammed into its detectors at somewhere around 60,000 kilometers an hour. An instrument called the Cosmic Dust Analyzer shattered those grains apart on impact and read off their chemical fingerprints in real time. What came back rewrote everything scientists thought they knew about this little moon. The plumes weren't just water. They contained salts. The specific kind of salts that only form when liquid water spends a long time in contact with rock, slowly leaching minerals out of it. They contained molecular hydrogen, a gas that, on Earth, is a telltale byproduct of hydrothermal vents, the undersea chimneys where scorching mineral-rich water pours out of the ocean floor and powers entire ecosystems that never see sunlight. They contained tiny silica particles that, according to laboratory chemistry, can only form when water is reacting with rock at specific warm temperatures deep below. And they contained organic molecules, carbon-based compounds, the basic chemical vocabulary that all known life is written in. Piece all of that together, and you get a startling picture. Underneath Enceladus's icy shell sits a global liquid ocean, salty, in direct contact with a rocky seafloor, very likely heated from below by hydrothermal activity similar to what happens on Earth's ocean floor. And that ocean has apparently been sending out chemical postcards for a very long time. The obvious next question is where the heat comes from, because this is supposed to be one of the coldest, most inactive corners of the solar system. The answer turns out to be almost entirely about orbital mechanics, rather than anything happening inside Enceladus itself. Enceladus is locked in what's called an orbital resonance with a larger neighboring moon, Dione. For every orbit Dione completes around Saturn, Enceladus completes exactly 2. That relationship tugs Enceladus's orbit into a slightly stretched non-circular shape, which means the moon's distance from Saturn keeps changing as it goes around. Saturn is a genuinely enormous planet, and as its gravitational grip on Enceladus varies with that shifting distance, the moon's interior gets squeezed and stretched over and over, orbit after orbit. That constant flexing generates friction, and friction generates heat, in a process astronomers call tidal heating. It sounds almost too simple to explain something this dramatic, but the numbers back it up. Researchers studying Cassini data estimate Enceladus is radiating something like 54 gigawatts of heat outward, roughly comparable to the combined output of 50 large power plants, generated purely by gravity-flexing rock and ice, with no nuclear reactor, no sunlight, and no internal engine of its own. What's more, newer analysis suggests this heat isn't only escaping from the South Pole where the geysers are. There's evidence it's also leaking out from the north, which matters enormously, because it suggests the moon's internal heat budget is more balanced and more stable over long stretches of time than scientists originally assumed. Stability is not a minor detail here. Chemistry alone doesn't build life. Chemistry needs time, long, uninterrupted stretches of stable conditions, where simple reactions can slowly ratchet up in complexity, generation after generation of chemical trial and error, until something crosses the line into self-sustaining, self-replicating biology. On Earth, that process took hundreds of millions of years even under ideal conditions. If Enceladus's ocean has stayed liquid and thermally stable for a large fraction of the moon's history, potentially billions of years, then whatever chemistry has been happening down there has had plenty of time to get complicated. Now here's where the story gets genuinely new, because everything up to this point was largely established between 2005 and the early 2020s. What happened in 2025 is that 2 separate teams went back into the Cassini archive, old data already sitting in storage for close to 2 decades, and looked at it with fresh eyes and better analytical tools. The most significant reanalysis focused on a single flyby from 2008, one that had always been unusual because Cassini passed unusually close to Enceladus, only about 21 kilometers above the surface, and unusually fast, with ice grains hitting the detector at nearly 18 kilometers per second, dramatically faster than most of Cassini's earlier passes through the plumes. That extra speed mattered enormously, because when ice grains hit the cosmic dust, analyze harder, they shatter more completely, and a more thorough shattering reveals finer molecular detail than a gentler impact ever could. Scientists had essentially been sitting on a higher resolution chemical snapshot for 17 years without fully processing what it contained. When the team, led by researchers including Nozer Khawaja and Frank Postberg at the Free University of Berlin, finally ran the full analysis and published it in Nature Astronomy in October 2025. They found the richest, most chemically diverse set of organic compounds ever detected in the Enceladus plumes. Not just the simple carbon compounds identified years earlier, but aromatic compounds, ethers, esters, and molecules containing nitrogen and oxygen woven into their structures. Families of chemistry that, on Earth, sit right in the middle of the reaction networks that build toward amino acids and the other essential components of biology. Crucially, some of these same molecules had already turned up years earlier in older, more degraded ice grains sampled from Saturn's E-ring, material that had been drifting through space and getting chemically weathered by radiation for a long time. What the 2025 study did was confirm that the same molecules exist in fresh material collected close to the source, grains that had traveled from the ocean floor, up through the icy crust, out through a geyser, and into a spacecraft detector in a matter of minutes. That distinction matters because it rules out the objection that these complex molecules were simply produced by years of radiation damage in space. If you find the same chemistry in material that's minutes old as in material that's been drifting for years, the simplest explanation is that the chemistry is coming from the ocean itself, not being manufactured after the fact by cosmic radiation. One of the study's co-authors put it plainly. The molecules found in this freshly ejected material prove that the complex organics Cassini had already spotted in Saturn's E-ring aren't just a byproduct of long exposure to space. They're readily available right now inside Enceladus' ocean. At almost the same time, a second team of researchers was working through a related but distinct question, and their findings, presented earlier in September 2025 and expanded later that fall, added an unexpected twist. Some of the organic molecules detected near Enceladus' surface, they argued, might not be coming up from the ocean at all. Instead, they could be getting created right on the icy surface itself, produced when high-energy radiation from Saturn's powerful magnetosphere slams into simple molecules sitting on the ice and rearranges them into more complex ones, including carbon monoxide, cyanate, ammonium, and even precursor molecules related to amino acids. At first glance, that sounds like it undercuts the ocean story, but it doesn't kill it. It complicates it in an interesting way. Even if some fraction of these molecules are being manufactured by radiation on the surface rather than rising up from below, they don't just stay there. The icy shell of Enceladus is geologically active. Material at the surface gets churned, buried, and eventually cycled back down toward the ocean over time. So whether a given organic molecule started its life in the hidden ocean or was cooked up by radiation on the ice above it, the endpoint tends to be the same. It ends up mixed into a long-lived body of liquid water in contact with rock. Either pathway feeds the same reservoir. As one researcher summarized it, there are competing hypotheses here, and that's simply how science works. Some of these organics probably do come from the ocean. Some might be manufactured at the surface, and figuring out the exact split is exactly the kind of question a dedicated follow-up mission is built to answer. There's another wrinkle in the story that came out of a separate 2025 analysis, and it's the kind of detail that keeps planetary scientists up at night. Enceladus' ocean, it turns out, may not be a single well-mixed body of water. Data suggests it could be layered, with different depths of water moving and circulating at different rates, and only slowly exchanging material with each other. That matters because any biological signature, a distinctive molecule, a chemical imbalance, anything that might hint at life, has to survive an actual physical journey to reach us. Up from a possible hydrothermal vent on the ocean floor, through however many layers of that ocean, through cracks and miles of ice, and finally out through a geyser into space where a spacecraft can sample it. If the ocean is stratified, the way the data suggests, a biosignature could get diluted, chemically altered, or effectively erased somewhere along that path before it ever reaches the surface. In other words, it's entirely possible for Enceladus to have living organisms thriving around a hydrothermal vent at its seafloor right now, this very moment, while the evidence of that life gets scrambled beyond recognition on its way up to where our instruments can actually detect it. The ocean isn't just hiding its secrets from us, it may be hiding them from itself, in a sense, burying its own clearest signals somewhere in the dark between the seafloor and the ice. That's part of why scientists are so careful about the language they use here, and it's worth sitting with the distinction, because it's the whole crux of where this research actually stands. Being habitable and being inhabited are two completely different claims. Habitable means the ingredients and conditions for life are present. Liquid water, the right chemical elements, a stable energy source, organic chemistry actively happening. On every one of those counts, Enceladus now checks the box, and checks it convincingly. Inhabited means something is actually alive down there, using that chemistry to grow, metabolize, and reproduce. Nobody has evidence for that yet, and the honest scientific position is that nobody claims to. As the lead author of the October 2025 study put it, researchers are confident these molecules originate in Enceladus' subsurface ocean, and that this strengthens the case for its habitability. But confirming habitability is not the same thing as confirming life. That gap between this place could support life, and life actually exists here, is the single most important open question left in the study of our solar system, and closing it is now considered one of the highest priorities in planetary science. Cassini itself can't answer that question. It was never built to. Launched back in 1997 with the technology of its era, Cassini was designed to survey the entire Saturn system broadly: rings, moons, magnetic fields, atmosphere, not to hunt for biological signatures with the kind of precision modern instruments allow. The mission ended in 2017 when engineers deliberately steered the spacecraft into Saturn's atmosphere to burn it up, partly to make absolutely sure it could never accidentally crash into and contaminate a potentially habitable moon like Enceladus with hitchhiking Earth microbes. That single decision, made purely out of caution, tells you how seriously scientists were already taking this moon's potential even years before the 2025 findings came out. What comes next is where things get genuinely exciting, because the instruments needed to actually settle the habitable versus inhabited question already exist, at least in laboratory form on Earth. Modern mass spectrometers offer orders of magnitude better resolution than what Cassini carried. There are laser-based instruments capable of detecting molecular chirality, essentially the handedness of a molecule, which matters because biological processes on Earth overwhelmingly favor molecules of one-handedness, while purely non-biological chemistry tends to produce an even mix of both. A strong chirality bias in a sample from Enceladus's plumes would be one of the more compelling indirect signs of biology that scientists could hope to find without literally seeing a cell. And there are also microscopy techniques sensitive enough to image individual cell-like structures directly if any were present in a collected sample. None of this is speculative future technology. It exists today, it just hasn't been sent to Saturn yet. That's exactly what mission planners are now working on. The European Space Agency has mission concepts in active development, aimed specifically at returning to Enceladus, with next-generation instruments built for this exact question, and the strengthened case from the 2025 findings has been described by ESA as directly reinforcing the argument for a dedicated orbiter and lander mission. On the American and private side, organizations, including the Breakthrough Initiatives, the same group behind large-scale efforts to search for signals from intelligent civilizations elsewhere in the galaxy, have floated dedicated Enceladus mission concepts of their own, with some scientists comparing the potential historical weight of such a mission to history's great voyages of discovery. Step back and look at the full inventory of what's now confirmed, and it's a genuinely remarkable list for a moon most people have never heard of. Liquid water in a global ocean that has likely persisted for a large fraction of the solar system's history. A rocky seafloor almost certainly in direct contact with that ocean, very possibly hosting active hydrothermal vents. All 6 of the core chemical elements every known form of life depends on: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. A genuine, sustained internal heat source generated by nothing more exotic than gravity-flexing rock, strong enough to keep that ocean liquid for eons rather than a geological blink of an eye. And now, as of 2025, direct confirmation of a rich, diverse, actively cycling suite of organic chemistry caught in ice that was, in some cases, only minutes removed from the ocean it came from. None of that guarantees life. It's entirely possible. Enceladus is a world with every ingredient for biology present, and still, for whatever reason, empty. Chemistry crossing over into biology may be rarer than we hope, even under near-perfect conditions. But for the first time, scientists aren't reasoning from theory or analogy about what a habitable ocean world might look like elsewhere in the galaxy. They're reading real chemical data, collected directly from an actual alien ocean, sprayed conveniently into space where a spacecraft could fly straight through it. Enceladus did something no other confirmed ocean world in the solar system has done. It opened a door and let us sample what's inside without ever having to drill through miles of ice. The spacecraft that will finally answer the last question, habitable or inhabited, hasn't launched yet. In some cases, it hasn't even been fully designed. But for the first time, scientists know precisely what to look for, precisely how deep beneath the ice they'd need to search, and precisely which instruments would need to make the trip. The moon keeps erupting on its own schedule regardless, plumes bursting from those glowing tiger stripe fractures every single day, carrying fresh chemistry up from a hidden sea that has been running in total darkness for longer than complex life has existed on Earth. Whether anything is actually alive down there in that darkness remains the open question. But after 2025, it is no longer a question anyone studying it treats as far-fetched. It's simply the next thing left to check.